Think about this for a second. Some of the biggest airplanes in the world, like the Antonov 225, have a staggering 32 wheels. 32.
Wow.
When you see these giants of the sky landing, that, reassuring thump on the runway, that's the job of these incredible tires. But you, like most of us, probably don't give them a second thought. Well, get ready, because we're about to dive deep into the surprisingly complex world of airplane tires.
Exactly. For this deep dive, we've got some fascinating material, a YouTube transcript and a detailed PDF. And our mission is, well, pretty simple, to uncover why these seemingly basic components are so utterly crucial and the truly extreme demands they face on every single flight you might take.
It's almost ironic, isn't it? These big black rubber rings look so, well, ordinary.
Yeah, just tired.
But they are absolutely fundamental to safety and the entire operation of an aircraft. Prepare for some genuine aha moments, because what these tires endure is, frankly, astonishing.
Consider this. The moment an aircraft lands, those tires go from a complete standstill to speeds of around 280 kilometers per hour, just in a blink of an eye.
Wow.
And the temperature shifts are just as dramatic. They're subjected to well below freezing temperatures at cruising altitude, only to heat up to over 200 degrees Celsius upon touchdown.
200 C.
Yep. So the core question we're exploring for you today is, how do these tires possibly withstand such brutal conditions without, failing?
Okay, let's start by unpacking what these incredible things are actually made of. You might think, well, rubber, of course, and you'd be partially right.
Only partially.
But aircraft tires are far beyond your average car tire. We're talking about a sophisticated blend of around 200 different materials.
200. What's fascinating here for you to consider is the sheer necessity of this complexity. This blend of different types of fabrics, specialized meshes, both natural and synthetic rubber compounds, and a whole range of chemical components isn't just for show, it's absolutely essential.
Essential how?
Well, it provides that unique combination of strength, from those meshes, flexibility from specific rubber compounds, and the crucial heat resistance needed to handle those extreme landing forces.
And those forces are, well, almost hard to comprehend. To give you a real sense of the sheer weight involved, picture a fully loaded Boeing 747-400. Its maximum takeoff weight can be around 395,000 kilograms.
395,000 kilos. If we connect this to the bigger picture for you, that staggering weight is equivalent to nearly 400 small cars.
400 cars?
Yeah, all concentrating their force onto the relatively small contact patches of those tires during takeoff and landing. Think about that immense pressure.
It's one thing to hear that massive number, but let's make it a bit more relatable for you. You know your car tires, right? Each one is probably supporting somewhere in the range of, 500, 700 kilograms.
Something like that, yeah.
Now imagine this. A single aircraft tire has to withstand the pressure equivalent to a staggering 10 tons. That's 10,000 kilograms at the precise moment it meets the runway.
10 tons. Per tire. This really highlights for you just how critical the intricate design and meticulous maintenance of these seemingly simple components are. The forces involved are just on a completely different scale.
Speaking of maintenance, these aren't tires that are going to last you years like the ones on your car.
Not even close.
They're changed based on the number of takeoff and landing cycles they've completed. And as you might imagine, it's the landing that really puts the most stress on them.
Yeah, that makes sense. The data indicates that, on average, a commercial aircraft tire might have a lifespan of around 350 landings.
350.
Now, depending on the airline's flight schedule, that could translate to anywhere from just 1 to perhaps 3 weeks in service. It gives you a sense of the constant cycle of checks and replacements.
1 to 3 weeks. And it's even more demanding for military aircraft, right? Their tires might only last for around 50 landings or even less.
50 or less, yeah. That really underscores for you the extreme conditions they operate under.
Definitely. Now, a brand new tire for a large aircraft, like a Boeing 777, isn't cheap. We're talking costs of up to €4,000.
$4,000 for one tire. Ouch. This significant cost is why retreading, or what's sometimes called recapping, is such a common and economically sound practice for airlines.
Right, recap.
It can cost around half the price of a brand new tire, effectively extending its useful life and reducing operational expenses. The process involves carefully removing the worn-out outer tread and bonding a new one to the underlying tire structure, typically done by the original tire manufacturer to ensure quality.
But there must be limitations for you to consider, right? They can't just retread forever.
No, Absolutely not. If the internal structure, what they call the casing, that's the main structural body of the tire, if that's damaged, then retreading wouldn't be a safe option.
Makes sense.
Then they'd have to invest in a new tire. This explains why airlines are so rigorous about inspections and frequent replacements well before they reach a point of critical wear.
Okay. This raises an important safety protocol for you to be aware of. If a tire happens to blow during landing, which statistically is the most likely time for a tire failure,
Right, peak stress.
the maintenance crews won't simply replace the one damaged tire. They will also replace the tire on the same axle, even if it appears brand new and shows no signs of damage.
Replacing both. That might seem a little unnecessary to you, wouldn't it? Kind of wasteful.
Well, the reasoning behind this seemingly cautious approach is that the sudden and extreme stress placed on the adjacent tire during the failure of its partner could have caused internal, potentially invisible structural weaknesses.
Ah, okay. Hidden damage.
Exactly. So, for absolute safety, it's deemed essential to replace both tires on the axle to prevent any future failures. It's a conservative measure, but one that prioritizes your safety as a passenger.
Makes perfect sense. Safety first. Always in aviation.
Now, you know that puff of smoke you often see when a plane first touches down on the runway? It's something I've always been curious about. What exactly is causing that?
Ah, yes, the landing smoke. That visible smoke you're seeing is actually the result of abrasion, pure friction.
Abrade.
Yeah. When the aircraft's wheels make initial contact with the runway surface, they aren't rotating at the same speed of the aircraft itself. They're basically at 0 RPM.
Right, they're stopped.
So they essentially skid or drag for a very brief moment until their rotation speed synchronizes with the plane's forward motion. That friction against the tarmac generates heat and causes wear, and that's the smoke you observe. Little bits of rubber burning off.
That makes perfect sense to me. I actually came across a really interesting bit of research related to this. A university study suggested that a remarkable 99% of that tire wear could potentially be eliminated.
99%.
How? If the wheels were spun up to the correct speed just before they hit the ground.
Wow. Pre-spinning the wheels. What's fascinating for you to consider here is the immense potential for increased efficiency and reduced operating costs. Pre-spinning the wheels could significantly extend the lifespan of these expensive tires.
You'd think they'd be all over that.
Well, that same study also shed light on why this seemingly straightforward system hasn't been widely implemented.
And what's the hurdle? It sounds like such a logical improvement.
The primary challenge lies in the fact that adding a motor, or the necessary mechanism to pre-spin the wheels, would substantially increase the complexity of the aircraft's landing gear system.
Ah, complexity and weight.
Exactly. This added complexity inevitably leads to an increase in overall weight, which in turn negatively impacts fuel efficiency and the aircraft's general performance characteristics. So it's a classic engineering trade-off.
A trade-off between potential long-term savings on tire wear and the immediate operational considerations of weight and complexity.
Gotcha, precisely.
Okay, let's shift gears a bit and talk about something else I found really intriguing. Why are aircraft tires inflated with nitrogen instead of just regular compressed air like in our cars?
Ah, nitrogen inflation. That's a critical safety feature designed with your well-being in mind. Nitrogen is an inert gas. It means it's significantly less chemically reactive than the mixture of gases that make up ordinary air, which is mostly nitrogen and oxygen plus other stuff. This inertness makes nitrogen far less susceptible to significant pressure and volume changes when subjected to the extreme temperature fluctuations that aircraft tires experience.
So what are the specific dangers for you if regular air were used? What could actually happen?
Well, regular air contains elements like oxygen and moisture. Under the extreme heat and pressure conditions inside an aircraft tire during landing or takeoff, these elements can react chemically.
React how? Like explode?
Potentially. This reactivity can lead to unpredictable and potentially dangerous expansion of the gas, significantly increasing the risk of a tire failure or even an explosive rupture, especially with the heat generated from braking.
Yikes. Okay, that definitely sounds like something you'd want to avoid at all costs. So nitrogen provides much more stable inflation pressure under those demanding conditions.
Precisely. But beyond just stability, nitrogen also exhibits better compatibility with the specialized rubber compounds used in the construction of aircraft tires, which helps to maintain the tire's structural integrity over time.
Okay, so it's better for the rubber itself.
Right. Additionally, nitrogen molecules are slightly larger than the molecules in regular air, which means that tires inflated with nitrogen tend to lose pressure at a much slower rate. The deflation rate is lower, contributing to consistent performance.
Less leakage.
Correct. And as a further benefit for you to note, because nitrogen is inert, it also helps to prevent corrosion of the metal wheel components. No oxygen, no moisture, no rust.
That's a whole suite of advantages for using nitrogen. Okay, now we touched on the incredibly high pressures these tires operate under earlier, but let's really emphasize that for you. We're not talking about the 30 or 40 psi you might put in your car tires, are we?
Oh, absolutely not. Forget car tire pressures. Typical inflation pressures for aircraft tires are well above 200 psi.
200 psi.
And in some cases, particularly for smaller, high-performance aircraft like business jets, the pressures can be even higher. These tires are specifically engineered and built to contain these immense internal forces.
And they're rigorously tested to withstand pressures far beyond their normal operating levels, right? I recall reading that they can endure pressures way past what they'd ever experienced in regular service, like crazy high numbers.
Indeed. Resistance testing has demonstrated that these tires can typically withstand internal pressures up to around 800 psi before they would burst.
800 psi, that's insane.
It's a powerful testament to the robustness of their construction. And here's an interesting safety measure for you.
Yeah.
During these high-pressure tests, they actually fill the tires with water instead of air or nitrogen.
Water. That seems a little counterintuitive to me. Why water? Wouldn't that just, like, slosh around?
It's not about operation. It's about testing safety. The primary reason for using water in these extreme pressure tests is safety. If a tire filled with highly compressed gas were to fail catastrophically during testing, the sudden release of that energy could be incredibly hazardous, potentially causing significant damage to the testing facility and posing a risk to personnel, shrapnel, shockwaves, the works.
Okay.
Water, being a liquid, is virtually incompressible. So if a tire were to fail during a water-filled pressure test, the release of energy would be far less violent and much more contained. It might split, but it won't explode outwards with the same force. It ensures a safer environment for the test engineers.
Ah, okay. That makes perfect sense from a safety perspective for everyone involved. Now, what about those fusible plugs I saw mentioned in our research? What's their role in all of this? Sounds important.
They're very important. These are ingenious little safety devices that are strategically integrated into the aircraft wheels themselves, not the tires.
Into the wheel. Okay.
Are specifically designed with a core made of a metal alloy that melts at a predetermined critical temperature. This feature is particularly vital during high-energy events such as an aborted takeoff or an emergency landing where maximum braking is applied.
Right, when things get really hot really fast.
Yeah, exactly. That heavy braking generates a significant amount of heat in the wheels and, by conduction, the tires. If that temperature gets too high, the tire pressure could increase dangerously.
So if the tires get dangerously hot due to extreme braking, what do the plugs do?
The fusible plugs are designed to act as a controlled pressure relief mechanism. When the wheel hub reaches that critical melting point, the alloy core melts, creating a channel,
A hole, basically.
allowing the highly pressurized nitrogen inside the tire to escape in a controlled manner, deflating the tire relatively slowly. This prevents a potentially catastrophic tire explosion due to excessive heat buildup.
So it deflates the tire on purpose to prevent a blowout.
Precisely, thereby minimizing potential damage to the aircraft structure, the landing gear, engines, wings, and reducing the risk of injury to people nearby from flying debris. It's a clever and crucial way to manage extreme thermal events safely.
It's just incredible to think about all these layers of engineering and safety features built into something that seems so simple on the surface. Who are the major players in this very specialized tire market? It can't be every tire manufacturer making these, can it?
No, you're absolutely right. It's a pretty concentrated market.
Right.
The aviation tire industry is dominated by 4 primary manufacturers: Goodyear, Michelin, Bridgestone, and Dunlop.
The big names.
The big names, yeah. Collectively, these 4 companies produce approximately 85% of all the aviation tires used worldwide.
85% just from those 4. And in terms of volume, how many of these specialized tires are we talking about being produced annually? It sounds like a significant number, but how does it compare to the sheer volume of tires made for cars?
Well, the production of around 1 million aviation tires per year might seem like a substantial figure.
1 million tires sounds like a lot.
It does, but compare that to cars. That 1 million actually only accounts for about 1% of the total number of tires manufactured for automobiles globally.
Only 1%. Wow.
Yeah. This really underscores for you the highly specialized and relatively niche nature of the aviation tire market. Different scale, different requirements entirely.
So we've discussed the stresses involved in landing and the impressive engineering of these tires. But what happens if a tire blows out during takeoff? That seems like a particularly precarious situation for you as a passenger to think about. More so than landing, maybe.
It is indeed a serious event, definitely up there with landing issues, and it's handled with utmost caution. The standard and immediate safety protocol in the event of a tire failure during takeoff is for the flight crew to initiate an immediate return to the airport of departure. No hesitation.
Okay, straight back. Now, as a listener, you might logically wonder why the aircraft wouldn't simply continue to its intended destination and have the tire replaced there. Seems easier.
Exactly. It would seem more efficient on the surface, wouldn't it? Just fly on and deal with it later.
But I'm guessing there's a very good reason they don't.
Absolutely. The overriding factor, as always in aviation, is safety. The flight crew has no way of definitively knowing if the initial tire failure caused any additional, potentially hidden structural damage.
Like what kind of damage?
Pieces of the tire could have struck the fuselage, the wings, damaged hydraulic lines, wiring in the wheel well, even ingested into an engine depending on the location. Continuing the flight with such unknown potential damage would introduce an unacceptable level of risk to everyone on board.
That makes perfect sense when you consider the potential for unseen damage. Better to be absolutely safe than sorry, especially when you're thousands of feet in the air.
Precisely. In some instances, as a further precautionary measure, the flight crew might even choose to leave the landing gear extended during the return flight.
Leave the gear down. Why?
It's a deliberate decision to prevent any loose debris from the damaged tire, bits of rubber or steel belts, if it's still partially attached to the wheel assembly, from becoming lodged in the wheel well during gear retraction. You don't want that stuff jamming up the works or causing more damage inside.
Okay, so keep it out in the open.
Right. Ultimately, returning to the originating airport allows for a controlled landing, usually overweight, which requires careful planning, followed by a thorough inspection of the aircraft and any necessary repairs on the ground. It is absolutely the most conservative and safest course of action in such a situation.
Wow. So from something as seemingly basic as a black rubber circle, we've uncovered this incredible world of complex composite materials, mind-boggling internal pressures, extreme temperature fluctuations, highly specialized maintenance procedures, and crucial safety features like nitrogen inflation and those ingenious fusible plugs. It's truly remarkable when you stop to think about it.
It really brings home for you the understanding that so much of what we often take for granted in modern air travel relies on incredibly sophisticated engineering at every single level, right down to the tires that meet the runway.
Yeah.
Something that appears so mundane is actually a critical and meticulously designed component of a very complex system built to withstand forces and conditions that are almost difficult to imagine in our everyday experience.
So, considering the immense stresses and the sheer level of ingenious engineering that goes into the creation of every single aircraft tire that allows these massive machines to safely take off and land, it really makes you wonder, what other seemingly mundane aspects of air travel, things we probably never give a second thought to as passengers, might be hiding similar levels of fascinating and vital complexity?
Like the galley carts, maybe? Or the seat cushions?
Exactly. It's definitely something to ponder next time you're waiting for your flight to take off.